So when we fail to reject the null hypothesis, remember that is a very weak decision. It doesn't let us say that the null is true, certainly doesn't let us say that we've proved the null, and it doesn't really even give us much information. It's simply an indeterminate decision. So far, we haven't collected enough evidence to reject the null. We've simply failed to reject it. All right, so while we're on the topic of beta, that is our type 2 error rate, and the fact that we couldn't know beta ahead of time, it'll hopefully make it a little bit more clear why we couldn't know it ahead of time by talking about statistical power, the sensitivity of our test. Notice that statistical power is the complement to beta. It is 1 minus beta, and it's the probability that if there really is an effect in the world, that we will reject the null hypothesis. So in this section, we're going to talk about first visualizing statistical power, because it's not on any of the diagrams I've shown you so far. Next, we'll talk about factors that affect statistical power. In fact, there are many factors that affect statistical power, so even in visualizing statistical power, we'll have to choose particular circumstances of the world before we can even calculate it. And finally, we'll talk about calculating power only briefly. This will be something we'll come back to using JUMP, and I'll even link to a video if you would like to calculate power by hand. I think it's illuminating to do this at least once, but notice that in real practice, we won't be calculating power by hand. We have software to help us do that. First, a definition. The power of a test is the probability that the test will reject a false null hypothesis. So power is the probability of detecting a real effect. This is the sensitivity of our test. But power here is not on any diagram we've seen. We've never seen that shaded region of a distribution where we would be rejecting the null hypothesis with a real effect. So far, we've only looked at the distribution of sample means when there isn't an effect, when the null hypothesis is true. And we've done this for an important reason. This is a distribution we can know before we do a study. It's incredibly difficult to think of what distribution we would know about a true effect and still be doing a study on it. If we knew what the true effect was in the world, if we actually knew what the effect size is for some treatment, we wouldn't be doing statistics. Statistics is helping us understand or make a decision about whether we think there might be a true effect in the world. So that's why we start off with this distribution, assuming the null hypothesis. That's something we can get a handle on. But to see power, we're going to have to change things around. To start this, I'll use this distribution, the distribution under the null hypothesis, and I'll shift it down to the left. Now what I'm showing you here is the distribution of our test statistic. That is the distribution of z sub x bar if the null hypothesis is true. And if the null hypothesis is true, this distribution is centered at 0, and I've left our shaded critical regions. So the region of this sampling distribution above 1.96 and less than negative 1.96. Just to keep things clear, I'm going to shade this distribution, and we'll be using some colors to keep track of what we're talking about. But for now, remember that this is the distribution of test scores we would get if the null hypothesis was true. Now let's consider a different distribution, the distribution of that test statistic if the alternative hypothesis is true. Now let's go back to our null and alternative hypotheses. Remember, the null hypothesis states that the mean after treatment is equal to the mean without treatment. And the alternative hypothesis states that the mean after treatment is just different from the mean without treatment. We said this before, but notice the alternative isn't specific. And for us to calculate power, for us to see power, we're going to have to play make-believe and pick what type of difference we are talking about, a specific difference that we are talking about. We can't test power for any possible alternative hypothesis. Instead, the amount of power of our test will depend on which alternative hypothesis. Now think about the coin flip example I gave you before. If you had a coin that was biased 1 flip out of 1,000,000, then we wouldn't have very much power or ability to detect that difference. But what if the coin was so biased that even on 10 flips, it would always come up 10 heads? Well, you would have considerable power to detect that difference. So the size of the effect is immediately going to be important. We'll talk about all these factors, but for our particular situation, the example we've been working with, let's imagine one specific alternative hypothesis being true. That is, let me take away our samples, because right now we're going to be talking about populations. And let's imagine that H1 is true in this particular way. That is, if we were to treat an entire population, the mean after treatment would be 120. So that is a huge effect. That would mean that on average, we would be raising people's IQ by 20 points. So this is a specific alternative hypothesis, and this is the one we'll use for visualizing power. So going back, if that were the actual effect in the world, what types of sample means, or specifically types of z sub x bars, would we be likely to get? Well, let's start by adding in an x-axis. So the center of the distribution of z sub x bar, if we're talking about it in x units, if the null is true, is a mean of 100. So this is what we saw before. We're likely to get sample means right around 100 if the null hypothesis is true. But we just picked a specific alternative hypothesis. What if the mean after treatment was centered at 120? Let's draw that distribution in. This is the distribution of z sub x bar if h1 is true in that specific way, with that one particular effect size. And notice that these are the sample means we're likely to get, and these are the sample z sub x bars we're likely to get if the alternative hypothesis is true in that particular way.